Hello and welcome to G Fun Facts Online. Today, we're traveling back in time, not with a time machine, but with science. We're going in search of ghosts. Not the kind that rattle chains, but entire worlds that have vanished from the face of the Earth. These are ghost ecosystems, sprawling, alien forests buried for 300 million years, bizarre oceans where the first complex creatures swam, and plains stalked by colossal reptiles. Through the incredible science of paleoecology and fossil geography, we can resurrect these lost worlds, piecing them together from the faintest clues left behind in rock. So how do you bring a ghost ecosystem back to life? It's like solving a puzzle with most of the pieces missing. The first clue is the rock itself. Fine-grained mudstone tells us about a calm, deep ocean floor. Coarse sandstone points to a fast-flowing river. Even tiny ripple marks preserved in stone can reveal the direction of ancient currents. Then there's the chemistry. By analyzing isotopes, different versions of elements like oxygen and carbon, in rocks or fossils, scientists can create an ancient thermometer, estimating past temperatures and rainfall. Zinc isotopes in a fossil tooth can even tell us if an animal was a herbivore or a carnivore. But the most important clues are the fossils themselves. Plant fossils, from microscopic pollen to petrified tree trunks, rebuild the ancient flora. Animal bones and teeth identify the creatures that roamed these worlds. But where we find these fossils is just as important. The continents are constantly moving. Understanding that North America was once a tropical landmass on the equator, or that it was split in two by a vast inland sea, is crucial to understanding the worlds these creatures inhabited. This is fossil geography, and it's our map to the past. Sometimes we get incredibly lucky. We find a fossil Lagerstätte, a German term meaning fossil storage place. These are rare sites where conditions were so perfect that they preserved not just bones and shells, but the exquisite details of soft tissues, skin, feathers, internal organs, and even stomach contents. These sites are true windows into ghost ecosystems. Our first stop is about 600 million years ago in the Ediacaran Period. Imagine an ocean unlike anything today. For billions of years, life had been almost entirely microscopic. Now, for the first time, large, complex organisms appeared. They were bizarre, soft-bodied creatures whose fossils are just faint impressions in sandstone. The seafloor was a quiet, serene place, covered in vast mats of microbes. Anchored to these mats were frond-like organisms called Crania, filtering nutrients from the water. Quilted, mattress-like creatures named Dickinsonia crawled slowly across the mats, absorbing food through their bodies. A recent chemical analysis found cholesterol-related molecules in a Dickinsonia fossil, confirming it as one of the earliest known animals. This world was simple. There were no real predators. Life was slow. But this tranquility was about to end. Towards the end of the Ediacaran, a new kind of animal appeared, the ecosystem engineer. These were the first burrowing animals. They tunneled through the microbial mats that had stabilized the seafloor for eons. This single new behavior, called bioturbation, fundamentally changed the world. It stirred up the sediment, destroying the firm ground the Ediacaran creatures relied on, and changed the water chemistry. Whether these new engineers outcompeted the old guard or simply destroyed their habitat, the bizarre Ediacaran ecosystem vanished, making way for a world that was far more familiar and far more dangerous. Our next stop is the Burgess Shale in the Canadian Rockies, a spectacular Lagerstätte from about 506 million years ago. It gives us a stunning glimpse into the Cambrian explosion, a period of rapid evolution when most major animal body plans we see today first appeared. The Burgess Shale was a deep-water marine environment at the base of a huge submarine cliff. Periodic mudslides would sweep down this cliff, instantly burying the community below and preserving them in exquisite detail. And what a community it was. Predation was now a major evolutionary force. Here we find Anomalocaris, a formidable creature up to a meter long, with sharp grasping appendages and a circular jaw. It was one of Earth's first apex predators, likely hunting the armored trilobites that scuttled on the seafloor. The diversity was mind-boggling. There was Opabinia, with 5 eyes and a long, nozzle-like claw on its face. There was Hallucigenia, a worm-like animal that walked on stilt-like spines, with another set of spines on its back for defense. The very existence of armor and defensive spines is clear evidence of the intense predator-prey arms race that was now underway. By analyzing the shapes and functions of these creatures, scientists have reconstructed a complex, multi-layered food web with predators, filter feeders, and scavengers. The ghost of the Burgess Shale shows us that the basic structure of modern marine ecosystems was already in place over 500 million years ago. Now let's jump forward to 300 million years ago, to the Carboniferous period. Picture a world of perpetual twilight under a dense canopy of strange trees. The air is thick with moisture and contains 35% oxygen, compared to our 21% today. This was the age of the great coal forests. At this time, the continents were crunching together to form the supercontinent Pangaea. The land that would become Europe and North America sat on the equator, experiencing a warm, humid greenhouse climate perfect for vast, swampy wetlands. But the plants here were alien. There were no flowers or modern pine trees. The forest was dominated by giant club mosses like Lepidodendron, reaching over 100 feet tall. Giant horsetails and tree ferns made up the understory. These forests were so productive that they changed the entire planet. When the plants died, they fell into stagnant, oxygen-poor swamp water where they couldn't fully decay. Over millions of years, immense layers of this plant matter, or peat, built up. Later, they were buried and compressed, forming the massive coal seams that power our world today. This process, burying huge amounts of carbon, pulled massive quantities of carbon dioxide out of the atmosphere. This led to global cooling and even glaciation in the southern hemisphere. At the same time, all that photosynthesis pumped the atmosphere full of oxygen. This high-oxygen world allowed land-dwelling arthropods to grow to terrifying sizes. We find fossils of Arthropleura, a millipede-like creature that grew up to 6 feet long, and Meganora, a dragonfly with the wingspan of a hawk. The ghost of the Carboniferous is a world built by plants, an ecosystem that literally re-engineered the planet's atmosphere and climate. For our final stop, let's visit perhaps the most famous ghost ecosystem of all, the final world of the dinosaurs. We're in the Hell Creek Formation, a stretch of rock in the American West that dates to the very end of the Cretaceous period, 66 million years ago. At this time, North America was split by a great inland sea. The Hell Creek ecosystem was a lush, subtropical coastal plain to the west of this seaway. It was a floodplain with rivers and swamps supporting ferns, conifers, and now a wide variety of flowering plants and trees, including palms. This was the kingdom of legends. At the top of the food web stood Tyrannosaurus rex, the bone-crushing apex predator. The dominant large herbivores were massive herds of the three-horned Triceratops and the duck-billed Edmontosaurus. The heavily armored Ankylosaurus browsed on low-lying plants, defended by its bony plates and tail club. But it wasn't just them. The ecosystem was filled with smaller ostrich-like and bird-like dinosaurs, crocodiles, turtles, fish, and the first mammals, which were small, shrew-like creatures scurrying through the undergrowth. Scientists reconstruct this world by taking a painstaking census of every fossil. They analyze the abundance of different species to figure out if Triceratops and Edmontosaurus ate different plants to avoid competition. Chemical analysis of their teeth helps confirm who ate whom. The Hill Creek Formation captures a vibrant, complex, and successful ecosystem, right up until the very moment it was violently erased. The end is marked in the rock by a thin layer of dust containing high levels of iridium, the calling card of the asteroid impact that ended the age of dinosaurs. As vivid as these resurrected worlds are, we have to remember we are seeing them through the hazy veil of deep time. The fossil record is incomplete. For every creature fossilized, countless others vanished without a trace. These ghost ecosystems are spectral images, built on evidence, but also on inference and scientific debate. They are not perfect photographs. Yet, for all their incompleteness, bringing these lost worlds back to life is one of the greatest achievements of science. It allows us to see how ecosystems are built and how they collapse, and to witness the incredible resilience and creativity of evolution over billions of years. By chasing these ancient ghosts, we learn not just about the past, but about the fundamental rules that govern our own living planet today. Thanks for listening to G Fun Facts Online.